Vector addition. Before we proceed with vector addition, let's review first some terms. The first term would be resultant. Resultant is the name given to the sum of two or more vectors. And then, since we are talking of vector addition, we will have the following expression: vector C being the resultant is equal to the sum of vector A plus vector B. Now let's put that expression into application. Draw and label the vector sum A plus B. So we have three figures, and we will graphically decipher vector C. So for number 1, as you can see, the two vectors, vector A and vector B, are sharing the same point, or their tails are at the same point. So how can we obtain vector C? To obtain vector C, what I will do is I would copy the length of vector B. Okay. Oops. I would copy the length of vector B. Okay. And then I would call it B prime, to know that this is just a parallel image of vector B. And then to get vector C, what I will do is I would connect from the tail of vector A. I would draw the tail of vector A up to the head of the shadow, or the parallel image of vector B. So this is actually our vector C. Okay, so this is our A plus B. Now for number 2, the same procedure will be done. Okay, so but this time, instead of making a parallel image of vector B, I would make a parallel image of vector A. Sorry about that. It keeps on doing that. So I would name this as A prime. Now to get vector C, what I would do is, again, from the tail of vector A to the head of this one. So that would be my vector C. Okay, noting that A is just the same as A prime. Okay, now for number 3, the vector sum for this one, I would replicate B So if B would be connected to the head of A, it would be something like this. Okay, and as you can see, that B and B prime are of the same, and A and B prime are actually the same in magnitude but opposite in direction. So that would give us the idea that the vector sum for in this case is equal to 0. Now let's proceed with the vector components. Let us determine the numerical values of the x and y components of each vector. So in this case, vector A has 5 units of magnitude, and it is directed 130 degrees with respect to the x-axis. So when we plot that to a Cartesian plane, we could see that it is plotted on the second quadrant. So what does it tell us? It tells us that the components of vector A would have the signs of negative and positive. Okay. Now this side would be the y component, then this part here would be the x component. Now what would be the angle for this one? Let's name this theta. Okay, so to get theta, that would be 180 degrees minus 130 degrees. Okay, so that would give us a value of 50 degrees. Okay, now how can we solve for the components? Now to solve for the components, we will be utilizing a mnemonic in trigonometry, which you are all familiar. It goes like this. We would use SOHCAHTOA. Okay, so if we want to find the x component, the x component can easily be obtained by using the cosine relationship. Okay, so cosine theta is actually equivalent to ax over the magnitude of vector A. Therefore, ax is equivalent to the product of the magnitude of A multiplied by cosine theta. And since we have figures for the magnitude and for the direction, we can also have an exact value for our ax. Okay, cosine 50 here is actually equivalent to 0.64279. So we will now have a value for AX roughly equivalent to 3.2139. Now, what about the y component? For the y component, we will use sine. Okay, but before we proceed with the y component, let's be mindful that the x component is lying on the second quadrant, so therefore it should be written as negative 3.2139. Okay, then going back, for the y component, we have sine theta equals to ay all over the magnitude of a. So to solve for ay, we will have the magnitude of a multiplied by sine theta, and substituting the given sine 50. What is sine 50? Sine 50 is equivalent to 0.7660. So if we multiply that by 5, ay would be equivalent to 3.8302. So to make it more readable, our AX is negative 3.21 and our AY is 3.83. Okay, now let's proceed with the next example. Okay. Now this time our vector can be found at the third quadrant, and our vector is vector B, and it has a unit or a value, or sorry, or a magnitude of 4, and it has a direction of 30 degrees below the negative x-axis. So since vector B is located at the third quadrant, we can say safely that the signs of its component would be both negative. Okay, so in this case we will draw, this would be by, and this part would be bx. So again, bx could be solved as the magnitude of b multiplied by cosine theta, and theta here is 30 degrees. So to solve for b, or to solve for the x component of b, we have 4 times cosine 30. Cosine 30 is 0.866 times 4. So we will have a value of 3.46. Okay, but since it is located at the third quadrant, bx is negative 3.46. Now for by is the absolute value or the magnitude of b multiplied by sine theta, which is 4 sine 30 degrees, and sine 30 degrees is actually 1/2 or 0.5. So that will just give us 2. And as we have seen, again, it's on the third quadrant. So by is negative 2. So in this problem, the components of bx would be 3.46 and by would be negative 2. Now, for this example, I want you to solve for the x component of c and the y component of c. I will give you enough time to solve for their value. Okay, so I hope we will have the same answer for this one. The answer for cx, or the x component, is 3.54, and for the y component is negative 3.54. Alright, now let's see and investigate further the vector addition. The statement C is equal to A plus B. Suppose the blue arrow is vector A, this vector A, and we connect another vector, vector B. So the resultant vector, as what we have known from the head-tail method, would be from the tail of vector A to the head of vector B. So that would be our vector C. Now we have also learned earlier that each vectors has what we call the components. So if we would determine the components of A, okay, let's say this is the component of A, so this would be AX and this would be AY. Okay, now for B, this part here is going to be BX and this part here would be BY. So as you can see, the thing that vector C is made up of is actually the sum of the components of the other two vectors. What do we mean by that? Looking at vector C, this is actually the x component of vector C. Right? This is actually the x component of vector C, and this is the y component of vector C. So from the diagram, we could see that the x component is actually ax plus bx, and the y component is actually ay plus by. And if we want to solve for the magnitude of vector C, we can say that the Pythagorean theorem is very much applicable. So we will now write it as cx squared plus cy squared under the square root sign. Okay? Now, how can we obtain the direction? To obtain the direction, we can say that the direction would be this, theta. So, in that sense, theta is equivalent to, the most appropriate would be tangent, so inverse tangent or arctangent of cy all over cx. So in this method, we can express vector C in polar form. Okay? Now let's take some examples on how to use our newly acquired knowledge. Okay, a basketball player runs down the court following the path indicated by the vectors A, B, and C. The magnitudes of these three vectors are, for vector A is 10 meters, for vector B 20 meters, and for vector C 7 meters. So we want to find the magnitude and direction of the resultant vector. Okay, so from the image, I would attempt to draw the resultant vector. So from here to there. Oops, nawala. Yan. Okay, so that the red arrow is our resultant vector. So that would be A plus B plus C. Okay. And I would rename it, or I would name it as vector D, because I don't want to write it in that form. No, it's very long. So before we proceed, we must first determine the components. And as you can see, for vector A, vector A doesn't have an x component, right? Based on the image, vector A has 0 AX, because from the image itself, it only shows us that vector A is going down. Okay, so if it's going down, we can only say that AY is actually what? AY is negative 10 meters. It's negative simply because if plotted in a Cartesian coordinate system, that would be negative y. Now for vector B is angled at 45 degrees. So Bx, or the x component, would be the magnitude of B cosine 45, and that would give us 20 multiplied by 707, and that would give us a value of 14.14 meters. It so happens that By would also be of the same value because sine 45 has the same value as cosine 45. Okay, now for C, for vector C, okay, based from the image, we could tell that this is along the fourth quadrant. If it is from the fourth quadrant, we could say that the x-axis is positive and the y-axis is negative. So Cx is equivalent to the magnitude of C cosine 30. So that would give us 7 times cosine 30. Cosine 30 is 0.866 times 7. So this is approximately 6.06 meters. For Cy, we have the magnitude of C sine 30 degrees, but let's not forget that this is found at the fourth quadrant, so let's add the negative sign immediately, so we will not be forgetting. And sine 30 is 0.5, so we have negative 3.5 meters. Okay, so what is next? The next thing to do is to determine the x component of vector D. The x component is actually ax plus bx plus cx, which would give us 0 plus 14.14 plus 6.06, and the unit is meters. So dx or the x component of D is actually 20.2 meters. Now for the y component, it's AY plus BY plus CY. So that would give us negative 10 plus 14.14 plus negative 3.5 meters. No, not millimeters, meters. So negative 10 plus 14.14 plus negative 3.5. That would give us an answer of 0.64 meters. So to obtain the magnitude of D, we will have dx squared plus dy squared, and we will extract the sum of the squares. So we would have 20.2 squared plus 0.64 squared under the square root sign. So let's use the calculator. 20.2 squared plus 0.64 squared, we have 408.45 under the square root. So the magnitude of D is actually 20.21 meters. Okay, now what would be the direction? So we use theta, arctangent dy over dx. That would be arctangent 0.64 divided by 20.2. So theta would be approximately equivalent to 1.81 degrees, 1.8 degrees, okay, with respect to the x-axis. So the final answer here would be D, vector D in polar form is 20.2 or 20.21 meters, 1.81 degrees, with respect to the positive x axis. Okay, so I hope this video would be able to help you solve some problems concerning vector additions by the use of components. See you next time.